So we've implemented the minting and burning of our stablecoin token. So people can deposit ETH and they get stablecoin token in return. And then they can use and burn the stablecoin to return ETH back. But we don't actually have this function for depositors to put extra ETH in. So that's what we do now. We implement a function for depositors, which will use the depositor contract that we implemented. And for that, let's first implement a private view function that we'll call get deficit or surplus in contract in USD. Private view, and returns us a number. And we'll need this private function here several times to basically figure out what is the current amount of surplus for the depositors. Because remember, the depositors will be the ones who will own the surplus. And we'll also need it to figure out, should the contract ever have not enough funds backing all the stable coins. So what is the deficit or surplus in the contract in US dollars? Well, it's ETH contract balance in USD, which is, so we first check the current balance of the contract just by address this dot balance, and we'll subtract MSG dot value. So then this here will basically tell us what is the amount of Ether in the contract before someone was calling a function here. And we'll subtract MSG.value because that's what someone is currently adding to the contract. And we want to know what was the balance before that. So we'll subtract MSG.value here. And then this is the amount of Ether. And now we want to have it in US dollars. So we can just do times Oracle.getPrice. Yes. And then we'll say UNT256 total stablecoin balance in USD, which is just the total supply. Because remember, the contract here itself is an ERC20, so we can just use the total supply state variable to check how many stablecoins are actually in existence right now. And then the deficit or surplus is an int 256 because it can be positive or negative. And it's basically the ETH contract balance in US dollar minus the total stablecoin balance in US dollar, which is just a total supply, but this is better to read. And we'll have to obviously convert it to int 256 so that the compiler doesn't complain here. And yes, we'll actually return int 256 here. And then we will just return this deficit or surplus. Okay, so this is the private function here that we can now use for our deposit function. So let's now implement the function deposit collateral buffer. And obviously, if someone is doing this, they are sending Ether. So this is a payable external function. And eventually he will receive the depositor coin token in return. So, but at the beginning now, we actually have to check this deficit or surplus. So we'll use this function we implemented, and we'll just say deficit or surplus in US dollar, and then use the function that we just implemented. And now we can check the deficit or surplus. So if deficit or surplus is in fact 0 or smaller than 0, then we have to do something special here. And yeah, let's return in this case early, and otherwise here, this would be the normal case. And in the normal case here, we will check, and it's surplus in USD. So we know that this is only when this deficit or surplus is positive. So we know this is actually a positive number. So just for clarity here, let's call it surplus in USD, and we can convert it into an unsigned integer because now we know, okay, it is in fact positive. So now we have to figure out what is the price of the depositor coin before we can actually mint it for the user. So let's calculate the price now, and we say DPC, so depositor coin in USD price. And let's make this with a private function again. So let's say get DPC in USD price, and we'll have to pass in the surplus here in USD. And then we'll actually implement this function, get DPC in USD price. So let's say function, and it receives the surplus in USD. And it's a private view function that returns the price. And then what is the price? Well, remember the depositor basically own all the surplus of the whole contract. So what is one coin currently worth? Well, it's exactly the depositor coin total supply. And this time we'll obviously have to make a contract call to this view function because it's not in the contract here, but rather a separate contract for the depositor coin. And that divided by the surplus in USD will give us exactly this price. And let's actually return it here, of course, and save it. So now let's actually use it, and we can use it here, this price now. So for the calculating the amount of tokens that we want to mint for the depositors. So there will be mint depositor coin amount equals msg.value divided by oracle.getPrice times DPC in USD price. So this will basically give us how many tokens we have to mint for this new depositor coin. And you can see here we use msg.value divided by the oracle price will basically tell us the amount in USD that this person deposited, and that times the DPC price in USD will give us the total amount that we have to mint. But one little thing here, of course, that we mentioned is we always want to multiply before dividing. So we'll actually do times DPC and USD price here to avoid the precision loss in Solidity. And then we can just call depositor coin dot mint and mint it to the sender and the amount we just calculated. And because depositor coin will be owned by this stablecoin here contract, we can actually call this mint function. But of course, this is the normal case when the depositor coin already exists. And now we have to implement the other case when deficit or surplus here is 0 or negative. So in the case when it's the first person actually calling this deposit, or even if the contract is actually in a negative and deficit, then we'll have to also figure out how much now to mint to this person. Well, first of all, we can also convert this int 256 in a uint 256, because we know this is now basically a negative number, and it represents the deficit in USD. So what we can just do is convert it to uint 256 and just multiply it with -1. Because now we know, okay, this is now a positive number, but it will represent the deficit. And we'll also need the oracle price again. So let's just get it and store it USD in ETH price oracle.getPrice. And we'll also need to note and now convert this deficit in USD and actually convert it into deficit in ETH. So that's just deficit in USD divided by the price, US and ETH price. And now we can calculate the new initial surplus in ETH first, which is basically MSG.value minus the deficit in ETH. Right, because this is the amount that we're sending now, and subtracted from that is what the deficit was, which in the case when it's the first depositor is actually just 0. But if it's negative, then the deficit here would be a positive value, not 0, and so this would be a little bit less now than your initial surplus in that case. And then we'll convert it into USD, so that's in USD is new initial surplus in ETH divided by the price. And now we can actually deploy a depositor coin. So this is the first time when this deposit collateral buffer is called. Or, like we said, when the contract is in negative deficit, we also basically destroy the previous depositor coin. And we do that by basically just deploying a new contract. And the old one technically still exists, but it's basically worthless and cannot be used in this contract here anymore. And then we'll calculate the amount that we want to mint depositor coin amount, as basically the new initial surplus in USD. And then we just mint a depositor coin dot mint to the sender and the amount we just calculated. And of course, we did a mistake here. We actually want to use the surplus in USD because this is basically what the depositor coins are, right? The amount they represent the surplus in USD. So this is the amount that we'll be minting here as well. And now if it actually turns out that this MSG.value, so the amount of Ether that the person was sending, is lower than the deficit, so basically the contract would be still in a deficit after the deposit, then this of course here would underflow and the transaction would revert. But to make it actually a little bit safer, let's add a little bit of a ratio for the first depositor so that he doesn't just deposit just enough and would be basically liquidated potentially immediately afterwards. And for that, we'll add a little safety check here. And for that, we'll just define a new ratio here in the state. So let's just make it a public function constant initial collateral ratio percentage. So let's just say 10% here. And of course, you might want to have a system where you can actually change this, but this is good enough for us now. And then in the deposit function that we just implemented, so here in the case where we just were in the first case or in the case of a deficit, we'll add an extra check here. That basically is required initial surplus in USD, which would be this ratio that we just defined, times the total supply, and because it's a percentage divided by 100. So in our case, when we actually defined this ratio here as 10, basically 10% means that the person who's depositing needs to have put in at least 10% of the current total supply. So if you think back to the case where there was a deficit, so here to get this contract out of the deficit, since there are 1,000 stable coins, you'll need 10% extra, so another $100 as safety margin. And then to actually check that we do have enough here in this case, we just convert this quickly into an ETH price. So in ETH, this is again just required initial surplus in USD divided by the USD in ETH price. And then we can do the actual check and see if MSG.value is less than the deficit in ETH plus the required initial surplus in ETH. And then we say stablecoin initial collateral ratio not met. So here, if you think back to this case here, where we have basically $250 deficit and think about 10% as the ratio, so you need $100 as for the safety margin, then this check here is basically checking that you do actually send enough Ether to, first of all, cover the deficit, and then have still enough left to cover the required initial surplus. And of course, I just realized that this has to be, of course, the other way around. We want MSG.value to be at least this size. So the require means this has to be true to continue. This is a common mistake, and now I did it myself. So always pay attention to the require statement here. You require this. And if it's not true, then you revert. So yes, we do require MSG.value to be at least this amount.